question. What if the acid was a limiting reactant? Meaning, what if the acid was the smallest entity? Does anybody know what would happen in that scenario or what that means? If the acid was a limiting reactant, what does that mean?
Dissolve the buffer region.
Yeah, some people got it. You've destroyed the buffer. So it's no longer a buffer. You've gone outside the buffer range, and in fact, you've made a critical error, which was the third case of the buffer, which was your buffer needs to have much more volume and really molarity than whatever you're adding to it. So you effectively have destroyed the buffer. The problem's over. Yeah. If you needed to find the pH, oh, this is also a fun question. If you needed to find the pH, it would kind of depend what happened. If this is left over, would you use the ice table, yes or no? If this is left over. No, it's a strong base. You just use like POH is negative log of OH minus or something like that. If this is left over in excess and none of this is, if this is the only thing left, you use an ice table and KB in order to solve it. So it depends what's left over, what you would do with it. That starts to get into some more of a titration type problem, but it could be fair game depending on the instructor and how they're feeling. But the concept is necessary to know. You're going to destroy the buffer. Okay, other questions, just specific questions? Yes? Yeah, sure. Favored and shift, clarify between those two. Let me just make up a reaction, it'll be a little easier. Okay. Favored. What side is favored? Products or reactants? Great, I asked here. Products or reactants favored? Products, what did you look at to determine that? Kc is large compared to the number 1. So I'm comparing Kc, or K just generically, versus the number 1 to get that. Is that okay? Okay, now, shift. Which way does it shift? Towards the products or towards the reactants? Q is less than K, right? If Q is less than K, which one does it shift? To the products. Is that okay? Okay, well make it okay by the exam, okay? So here I'm comparing K versus Q. Is that okay? So it's it's what you're comparing K to. 1, you're talking about favored. Q, you're talking about shift. Okay? Is there any scenario where the shift will go towards the reactants? Yes or no? Yes, if Q is greater than K. It was not in this scenario, but it could happen. Okay. Alright, is that good? Next. Yes? What about ionization? Like there's a reaction called the ionization reaction. There's the ionization energy. The percent ionization. Okay, I totally forgot about that one. Yes. Let's say we have a reaction. Let's just write it generic. Maybe I should be more specific. Let's do an acid, that'll be easier. I'm going to do acetic acid, sorry it's a little small. We're talking about percent ionization here. Okay, let's say we have a generic reaction. Again, you should be able to write this reaction yourself. The percent ionization, I'll write it down here at the bottom. This is a formula I typically don't give on an exam. It would be the value of X, which is, I'll write that out in a second, divided by the molarity times 100. What are those things? X is going to be the H3O plus concentration, which you get from the ice table, the E line, the equilibrium concentration. M is going to be the concentration of HA initially, and even afterwards, because if it's a weak acid, it doesn't dissociate. So this is from the I line. This is from I, the I line of the ice table. This is from the E line of the ice table. Is that okay? Technically, this is also, you could take it from the E line and get the same answer. Anybody, for an acid like this one, do you expect the percent ionization to be larger or smaller than 10%, say? Probably smaller. Anywhere between 0 and 10% typically. What does concentration affect the percent ionization? Yes or no? Yes, that is exactly what affects the percent ionization. See concentration right here. Okay, it literally affects it. Okay, that's what affects it. Okay, so what you're going to do to get this is you're going to have to do the ice table, you're going to have to find X, and then use this formula down there. Is basically what you're going to have to do to find it. You expect the answer to usually be between 0 and 5%, though it could be higher than 5. It can't be less than 0. Okay? Is that a good little summary? One thing I'd also watch out for is how to do this problem in reverse. It's a pretty classic problem. And you'll see a number of examples on practice exams and stuff like that. Okay, next. Yes, 1, 2, then 3, then 4. Okay, yes, 1.
What is the definition of a buffer?
The definition of?
A buffer.
Definition of a buffer, I don't know if I have, it depends how you want to define it. Not that there's multiple definitions, but you can look at it from different perspectives. A buffer is something that resists pH change. Is usually the classic, meaning that the center pH for a buffer is its pKa. So if I go over to the Henderson-Hasselbalch, which again is the buffer version of the ice table. Okay, so instead of using the ice table, you don't have to anymore. You can use the Henderson-Hasselbalch, which whoever your instructor is, me or somebody else, will give you this on the exam. The ideal pH of a buffer is the pKa, meaning the log of the base over the acid is 0. That second term is 0. That'll happen when the concentration of the base equals the concentration of the acid. B over A would just equal the number 1, and the log of 1 is 0. So, when the pH equals a pKa, that's the ideal pH for a buffer. And if you try to add something to a buffer, it doesn't want to change. So let's say that pH is 5. You add something to a buffer, maybe it'll change to 5.01 or 5.02, but it's not going to change to 6. So that's what a buffer does. A buffer, another way you can look at a buffer or define it is based on what it is. So a buffer is a weak acid and its conjugate weak base. Or you could say it from the reverse direction, a base that's weak and its conjugate acid, however you want to look at it. That base and acid have to have a similar molarity. So the base and its conjugate acid or the acid and its conjugate base have to have a really similar molarity within a factor of 10, approximately. So if that base has a concentration of 5 molar, the acid ideally is 5 molar, but it could be 2 molar or 1 molar. As long as it's kind of close, that's fine. So, conjugates that are weak, similar molarity, and a lot of it. That makes a good buffer. Is that good?
Yeah. Okay,
use that equation, you should be good. If you add anything to a buffer, you must do stoichiometry before using this equation. Okay, 2. You were 2? 2, yes. You can be 5 if we have time. Yes. What page are we on? 63 of my practice exam reader. I just want to show everybody. I don't know if I'll have time to do it all out, but I'll at least talk about it. Okay, you're talking about number 18? 17b, yeah. This is Spring 15, Exam 2, page 63. Okay. We want to write the reaction, is that what we're up to here? Okay. So I'm going to write this reaction, maybe if we do it like this. I'm writing B here. KCN, I would have accepted a couple possibilities here. You could have just gone like this. And then it's kind of like a double replacement, but this is the base and that's the strong acid. Because you have a strong acid, it's going to go forward 100%. You wouldn't have to write that number, but you probably want a single-headed arrow there. And you'll get HCN and KBr. That's one way you could have written it. If you got rid of the spectator ions, I would also accept that. How do I know KCN is the base? There's a couple ways. Just by default, if that's the acid, that has to be the base. Or a more proper way to do it is you go, oh, I've got K plus, I've got Cn minus, you know, acid, base, or neutral. And then that's KOH, I've got HCN. KOH is a strong base, so that means this is neutral. This is a regular acid, so that's a regular base. A neutral plus a base is a base. Is that okay? All right, on this? Okay. Potential. I don't remember how this quarter was graded in particular, but it's not a good idea if you have a strong here. So the question is, what if you put a double-headed arrow? You will be in danger of losing points, depending on how the TAs are grading it, if you have a strong acid or strong base in the reactants. Okay, number 3. Was there a question on this? No. Oh, number 3. Yes?
Page 70, number 12.
70. This is Spring 13, page 70, number 12 here. Just the setup, is that what you're looking for? Okay. This is a colligative properties problem. How do I know that? It talks about boiling point. It talks about something and something else that being so much above the boiling point. Definitely colligative. Okay? So, because we're talking about delta T equals IKM. Delta T is right here, because it's above the boiling point of pure benzene. We're adding something to benzene. It looks like these are all, or like molecular compounds. Sulfur, benzene, etc. They're all nonmetals. Probably I is going to be 1. That's going to be a great guess. K is right here. It's given. For benzene, that's the solvent. That's what it should be. Notice this is not a plug and chug problem because they want the number of sulfur atoms. That's that second scenario, the slightly harder one. You're solving for molality. Remember, molality is equal to mole per kilogram. It's going to be mole of the sulfur compound. I'll put SX because we don't know what it is, divided by the kilograms of benzene. Okay? So what you're going to do, oh gosh, sorry, that got off screen. What you're going to do, you know the kilograms of benzene, it's 40. You're going to drop that out, you're going to be left with the moles of sulfur. You got the grams of sulfur. You're going to go grams divided by moles. This is just conversion. Grams divided by moles. And then that's going to be a number larger or equal to 32. If you look at the periodic table, sulfur is 32. So if it equals 32, there's 1 sulfur. 64, there's 2 sulfurs, etc. Is that okay? This is a classic second case scenario of any colligative problem, where we solve for something within molarity or, in this case, molality. Okay? You're 4. 4. Keely, yeah.
Can you do number 2 exam, spring 2014
65. Are we talking about a multiple choice problem? Number 2. No, This one right here? Okay. We are going to, you could do a calculation here if you wanted to. I'll just explain it in words, okay? Hopefully this will do it for you. You could do a calculation, but you're adding an acid to an acid. So even though it is a weak acid, you're adding more protons. So you would expect there to be more H3O plus in solution. So I expect likely the pH to increase. Or, I mean, sorry, my bad. You'd expect that to go up a little bit. But however, in the molarity, something else is going to change. What's that? Yeah, that's the moles. That will increase. Anybody?
Volume?
The volume will go up or down? Up. Yeah, it's going to double. Whereas I don't think the H3O plus concentration will double. So the molarity should go down because of dilution, simply. Because you're diluting. So you should increase the pH slightly. Because you're diluting it. So the molarity of the H3O plus concentration will go down a little bit. Yeah. So you're adding a little H3O plus, but not as much as the volume change is going to be. Is that kind of okay? Okay. 5. Yes, we made it to you. Spring, hold up, 16, practice exam somewhere. Spring 16, number 17. Are you talking about this one? Okay. Like just the setup? Okay. So in this case, you have a reaction, you have a Kp. Just a solid is there. There's none of those. Total pressure, we want the sum of the EII, is what we're looking for. Great question. I'll ask the audience. What's the initial pressures of these? 0, because all there is this, which is the solid. So it hasn't, what phase change, anybody? What is the phase change? Sublimation. It hasn't sublimed yet. So it hasn't undergone sublimation, and so there's no gas once you introduce it, but soon, once it'll reach equilibrium, there'll be gas. Is that okay? Okay. Yes, a couple more. 1, 2, 3, 4. I don't know if I'll get to all of you. Yes. Spring 15. Just a second. Do you have a page number for me? What number? 14? 17? Wait, we were just there a second ago, weren't we? Uh-huh. Oh gosh. Oh, was it this? Okay, which reaction, acid or base? Oh, A or B, part A or B. Would you expect to have a very small? Oh, cool, I like this. Okay, what do you think? I'll poll the audience. Let's do B first. Large, because that's the one we did. Large or small K, anybody? For B. Large because? You got a base, strong base. Has to be large. It goes forward 100% whenever there's a strong here. Is that okay? So that was large. A, anybody? Small because? It's weak. It's weak acid. Is that okay? That's all I wanted. Yeah, there's no math. Yeah, it's just which would you expect. There's no math. Okay. Who's 2? Yes. 53. Okay. 53. Just a minute. Are you talking about a multiple choice problem here? What number? 6. Page 53. Winter 18. Okay. What's the okay, this one, right? Okay, what's the pH of the flowing solution? I'm going to add this to a buffer. What kind of math am I going to do here? You would do stoichiometry and then Henderson-Hasselbalch, or if you want to make life easy, no, ice table makes it harder. I've heard of ice. If you want to make life easy, the pH is going to go up or down. Down, why? Strong acid. Is it going to go down a lot or a little? A little, because it's a buffer. So pick the number below 5.09 that's not a lot below it. That one. I wouldn't do the math because you can. You totally can. You should get this answer or a number close to it. I don't have time to do it now, but it's you're gonna write the base plus this acid. You're gonna do stoichiometry. After the stoichiometry, you're gonna put it in the Henderson-Hasselbalch. That's what you would do. But it's a waste of time because it has to be that answer. This is in the concept section of my multiple choice. So you know there's minimal math. In the concept section, at most, you're going to take your calculator and add or divide something or something like that. At most. This is too much work for a concept question. I purposely put numbers to make people do math, and then they can go, haha, I wasted so much time. Okay, 3, 4. Yes? Spring 18. Number 3, a multiple choice. Number 12. This one right here. This CDP problem. Okay, this is page 49, spring 18. Okay. The pH of the dissociation of this. So pKa is 6.7. What's the initial ratio? I know the pH is 8.7. So if I write my formula out, it's a buffer. I know it's a buffer because I've got conjugates. And I think it even uses the word buffer in here. There, buffers. Oh, and buffer here. Oh my gosh, it's everywhere. Okay, the pH is 8.7. This is 6.7. So that's a difference of 2. So 2 equals the log of the base over the acid. If you take this, you're going to get 100 to 1 for this ratio. Is that okay? Oh, I can zoom out. This ratio will be 100 to 1. Is that okay? Okay. You were number 3, 4? Yes? Spring 16 is what I'm flipping to. Is you're talking about a multiple choice problem? This one, here we go. Okay. They're all the same molarity. This is a classic type of colligative properties problem. What you're going to do, maybe I can kind of put it up here, like this. You're going to take all these molecules, wow, there's too many to write down. Oh my gosh. I'll just write down 2 of them, okay? There's others. You're going to take the molecule. You know the formula is delta T equals IKM. You want to find the one that has the lowest temperature as a liquid. That means the highest delta T. So you're looking for the largest value of this. You're going to compare I, K, and M for all of these. For M, it says in the problem they're all the same. For K, they're all aqueous. They're all the same. They're all for water. So whichever one has the highest I value is the one with the largest delta T. Is that okay? That's it. So it's asking for I in a weird way, but fun. Okay, I think I can do, was there a person after 4, 5? Yes, last one. What page? 67. What number? Oh, this one right here. Okay. Let's see if I can, I'll just rewrite it. I want to know if this is acidic, basic, or neutral. It's CH3NH3Br. Yeah. So you're going to separate them out into this, like you always do. Then the conjugate of this is HBr, so this is a strong acid, so this is neutral. The conjugate of this is going to be CH3NH2. You're like, what the heck is that? If you don't recognize it, it's just a base. So this must be an acid. This is a regular base. So this is acidic. Is that all right? A question on this? Yeah. Yeah, you could have, this is the same as writing this. So 3. That's the same thing. It would be like the conjugate ammonia and NH3, NH4 plus the conjugates. Ammonia is the same thing as writing NH4OH. It's just this plus water, one more H2O, so it doesn't matter. However you want to think about it. Okay, I need to close up shop. The custodians probably want to clean this place up. Hope you have a good night. And I will see my class on Tuesday.